Okay, so this is day 3 of our thermochemistry unit, and will be again in probably 2 parts. And we'll start with Hess's law. So what do we have here in terms of the Hess's law is that if we refer back to that state principle that we have, like final and initial, it doesn't matter what is happening in between. If we know the in between, then we can figure out the total. So the law of conservation of energy, because of the law of conservation of that, the heat of reaction is the same whether the reactants are converted to the product in a single reaction or in a series of reactions. The first one to came up with this suggestion, which now is known as the law, it's Hess in 1840. And what he was saying that if 2 or more thermochemical equations are added to give up a final enthalpy, final equation, then the enthalpies can be added to give the enthalpy for the final equation. So final answer according to the placeholder rule. Sometimes the heat of reaction for the chemical reaction is not easily measured due to the time of reaction, cost, how rare the reaction is happening, and so on. So then in those cases, what do? Is we use the Hess's law to calculate the change of enthalpy of reaction. So the very first step is that we will have a right reaction. So steps. Step 1 is we'll have a balanced reaction. If it is not given, then we have to balance it. Usually, chemistry is pretty good. It's given balanced. But if it is not given, then then the next step will be to manipulate the given reaction so that we'll manipulate those intermediate reactions to give us a net reaction that is the same as what we are looking for. Manipulate intermediate reactions to give us the net reaction that we are looking for. Okay. And then if you are reversing the direction of the reaction, if you reverse the direction of the reaction, then you reverse the sign of change of enthalpy. And then the fourth rule is if the coefficients are used in the chemical reaction, then you apply the same coefficient to the change of enthalpy, and then you just add and cancel out. Add that change of enthalpies and cancel out. And cancel out reactants and products. To have the final net equation. Okay. So let's see what is happening here. Let's suppose that we have carbon and oxygen to find what is the enthalpy of formation at SATP condition for carbon monoxide. The reaction is carbon and oxygen are giving us carbon monoxide. The intermediate reaction is that carbon and oxygen forms carbon dioxide, and then carbon monoxide and oxygen form carbon dioxide. So now, the main or the net reaction, the focus reaction will be this one here. Carbon and oxygen will give us carbon oxide. So what do? Is we flip the first one. No, we flip the second one. We flip the second one. By flipping the second one, so whatever is on the reactant becomes a product, and whatever was a product becomes a reactant. Because the first reaction here has carbon dioxide on the product side, so we need that to be in the reactant. And by doing so, we flip the sign of the change of enthalpy of the formation, okay, from negative into positive. So we have 2 is this one here. Now, when we divide it by 2, why do we divide it by 2? Because we have 1 carbon dioxide here. So we need to have 1 carbon dioxide here. When we divide by 2 every coefficient, then we will divide by 2 even the change of enthalpy of formation at SATP condition. Then what we have as the flipped divided reaction for reaction 2 will be carbon dioxide is giving us carbon monoxide and half mole of oxygen with a molar enthalpy of formation of positive 283 kilojoules. Now, when you add those together, carbon dioxide and carbon dioxide is cancelled out. And then we have 1 mole of oxygen on the reactant and half mole of oxygen in the product. So 1 mole of oxygen in the reactant and minus, because it's in the product, 1/2 mole of oxygen on the product will give us 1 mole of oxygen in the product side, which actually is what we were even having in our focus equation. And then just by simply adding negative 393.5 and positive 283 kilojoules, we'll have a formation, a change of enthalpy of formation of negative 110.6. Okay. So when we see the little degree symbol, that means standard at SATP conditions, which as we at the last part of the day 2, we have it is an SATP condition, which is 25 degrees Celsius and 100 kilopascal. And all this change of enthalpy of formation can be found on pages 4 and 5 of your data booklet. And then, as I said, is if you are doing formation, so when we are calculating it, you can see the formation of a certain element or a certain compound into that table, and then is cancel out, do the math. Keep in mind that a positive is stays positive, a negative is a negative. So you just add the enthalpies together. So let's see an example another example here when we have that to determine the enthalpy of combustion when we have those middle equations here. Okay, I will give you like few minutes and then you can watch the video and see. I will suggest you to stop it, do it, try it on your own and then do it. So let's start with the main equation is that propane is combusted with oxygen, so it's going through combustion and is producing carbon dioxide and water. So now if we see the intermediate reaction, we'll have carbon and hydrogen forming propane. We want propane not on the product side, but on the reactant, so we flip it. So equation 1 will become C3H8, and then as a product, we will have 3 carbon plus 4 H2. And now the change of enthalpy of formation is negative. In the reaction, since we flipped it, will be positive. Positive 103.8 kilojoules. Okay, now the other one is that carbon dioxide here is in the product, carbon dioxide is in the product, and we will keep it as it is. So carbon plus oxygen will form carbon dioxide. And the enthalpy of formation will save the sign. However, if you notice here in the focus reaction, we need to have 3 carbon. So what I will do immediately, I will multiply it by 3, and this will be 3 times negative 393.5. Okay. Water, that is the other product that we have in the focus reaction, is as well in the product, so it's on the same side as the focus reaction. So we will save it as it is. Plus 1/2 oxygen gives us H2O gas with the enthalpy of formation at standard conditions as a negative 241.8 kilojoules. Good, so now if we add all of those together, then we will see that 3 carbons are canceled out, correct? Then we will have 1 hydrogen here and 4, oh, we have 4 hydrogens. See, this is something. Okay, so 4, 4, 4, and then this will be 4 times negative 241.8. So 4 hydrogens and 4 hydrogens are canceled out. Then 4 times 1/2 is the same as saying 2. Okay, so now what do we have in the product side, in the reactant side, sorry, is propane plus 2 oxygen that we have here plus 3 oxygen is equal to 5 oxygen. And then in the reactant, nothing on this, 3 carbon dioxide and 4 water, which is the exact equation that we were focused and wanted to deal with. Now the combustion of the reaction will be whatever is the change of enthalpy from the first equation, second equation, and third equation. So it will be exactly positive 103.8 kilojoules plus 3 times negative 393.5 kilojoules plus 4 times negative 241.8 kilojoules. And if you do the math, you should have 2000, negative 2000, 2043.9 kilojoules. So now, as it says, suggest here, try to, in your workbook, questions 1 to 5, and also on your textbook, pages 508, 509. Also in class, so we will try a lot of Hasse-Low problems. So, but just keep in mind that the focus will be the focus equation that we want to. We will switch the products and the reactants, and when we are switching them, we will switch the sign of the change of enthalpy, and then we will add, cancel to have the focus equation by adding, cancel, by adding the change of enthalpy of intermediate equations. Now, when we see the formation, what do we see on pages 4 and 5 are the molar formation. So the amount of, let's suppose that we have aluminum oxide. We have in our data booklet is a negative 1,675.7 kilojoules per mole. When we balance it, so when we balance it, we have 2 aluminum. What we see, or what do we have to have, is that the balance equation has to be for the compound that we're finding or what we are referring at, it has to be 1. So when we see the reaction, let's suppose that we have aluminum solid plus oxygen gas will give us aluminum oxide. Then if we were going to balance it, we would have 3, 2, and 4. However, when we are looking for the molar enthalpy of formation, and our data booklet is a molar enthalpy of formation at standard condition is a negative 1675.7 kilojoules per mole. So this is not the proper way of expressing it, because if we are saving it as an equation, then we have to multiply this by 2 times. But if we are writing it as the number of moles for aluminum oxide is 1, then everything will be divided by 2. So 4 over 2 is 2 aluminum plus 3 over 2 oxygen, and will give us a 1 aluminum oxide in the solid form. Then we can write the proper number for the formation, molar formation of aluminum oxide as negative 1675.7 kilojoules. So if we are writing it as a molar formation, then we will write it with the number that the page 4 and 5 is giving us. And if we are writing it as the reaction, then we will multiply it by whatever is the number of moles in front of the compound that we are looking for. And if it is high number of negative, then that means that we have um, a very stable compound. When we are looking at the decomposition, then we see the sign instead of the sign that the table 4 and 5 on pages 4 and 5 is giving us has to be the opposite. So if you see in your data booklet on table 4 and 5, page 4 and 5, you will see that nitric acid is the enthalpy of formation for nitric acid is a negative 174.1 kilojoules per mole. But when we are finding the composition of nitric acid, composition, simple decomposition, not composition, decomposition, then this will be positive 174.1 kilojoules per mole. Okay, so when we are writing the equation as a simple one, so 1 mole of nitric acid is decomposed into hydrogen and nitrogen and oxygen. They're all gas. The coefficient here has to be 1, which means that we will have half of hydrogen, half of nitrogen, and 3/2 moles of oxygen. So now when we have for 1 mole, we will have a simple decomposition, change of enthalpy, molar enthalpy of positive 174.1 kilojoules per mole. If we are looking for a different number of moles, then we will multiply that number 174.1 by whatever the number of moles we are looking for. If it was 2, then multiplied by 2. In our case, is 6.41, and this is what we why we multiplied by 6.41. So if we are going to define which one is most stable or not, we have to look to the more negative one. The one more negative will be most stable. So on the first one, we have silver iodine. Silver iodide is negative formation is negative 61.8 kilojoules as the molar enthalpy of formation. And the next one is a silver chloride, which is negative 127.0 kilojoules per mole. And then we have nitric acid. Nitric acid is a negative 174.1 kilojoules per mole. And then we have propane, which is negative 103.8 kilojoules per mole. So the more stable is the more negative. So the more negative here is nitric acid. So then next one is silver chloride. So then next one is propane. And the last one, the last stable one is silver iodine. Or if we are using numbers, then it will be 3 2, 4, and 1. I hope that this makes sense.